So in this video, I'm going to discuss various mathematical representations or functions that can be used to model the continuous time impulse signal or the Dirac delta function. So I'll start with a little bit of background on the Dirac delta function. So it has two defining properties. The first one is that its integral is equal to 1, and the second one is that its integral of a product with a function is equal to the function at t equals to 0. And these two properties can be realized if the Dirac delta function delta of x is 0 for all non-zero x, and it tends to infinity, that is it diverges at x equal to 0, and it is graphically represented by an arrow at t equals to 0. um, so here are the mathematical representations that I'm going to cover in this video: the rectangular pulse, Laurentian, Gaussian, and one integral representation. So let's start with the rectangular pulse. Um, this one is quite simple and is used quite often in signal processing, and it is just a rectangular pulse centered around t equals to 0, and it is really easy to see why its integral is equal to unity, thus satisfying the defining property of the Dirac delta function. And at the limit a tends to 0, it strongly diverges at t equal to 0 and is 0 for all other values of t. uh, in essence, what happens is that the rectangle keeps becoming thinner and thinner, and taller and taller. So its advantage is, of course, that it is quite easy to deal with and can be represented by this piecewise function, but it does have discontinuities and non-differentiabilities at 2 points. So it is not viable for cases um, where we need analytical results, or where we are performing analytical or mathematical calculations. Um, so the next slightly better representation is the Laurentian, which is a smooth curve, so which is obviously an advantage while dealing with mm, mathematical tools, and it can be integrated, and it is seen that its integral is also equal to 1, so it is a good candidate for um, modeling. It is a good candidate for representing the Dirac delta function, and it is peaked at x equal to 0, and at the limit a tends to infinity, it also strongly diverges at, sorry, it is peaked at t equal to 0, and in the limit a tends to infinity, it will diverge at t equal to 0. And the most important use of this representation is that its Laplace transform can be calculated easily, and therefore it is quite useful when dealing with Laplace transforms. The next representation is the Gaussian, which is quite familiar distribution, um, and it is also a smooth curve which is peaked at t equals 0. The peak is somewhat less sharper than the Laurentian distribution, as can be seen, but its integral can also be calculated, and using this formula for the Gaussian integral, and it is seen that the integral is also equal to 1, and also that it at a sorry and that at t equals to 0, it diverges strongly and is 0 at all other t. um, and the most important use for it is both Fourier and Laplace transforms, because of this exponential form. It can be easily incorporated into Fourier and Laplace integrals. The integral representation is quite useful when dealing with Fourier transforms specifically, because this representation features a complex exponential integral of a complex exponential, and it is obvious why it is useful when dealing with Fourier transforms. This can be integrated to give this representation in this sinusoidal form, and it can be plotted, and in the plot it can be seen that this representation is also a smooth function and diverges at t equal to 0 in the limit a tends to infinity. And um, in so as I said, it is quite useful while dealing with Fourier transforms. In fact, It is also used to construct a proof for the formula of the inverse Fourier transform. Its only disadvantage, however, is that since it is a complex exponential, the integrals might require some familiarity with complex analysis or contour integration, and even the proof that this representation, the integral of this representation, is indeed equal to 1 requires the use of contour integration. So these are not the only representations that are available for the Dirac delta function. Other representations which are slightly more complicated, like the representation in terms of Legendre polynomials or Hermite polynomials, or the series representation also exist. But these are not aren't used in signal processing generally, and these representations find their uses mostly in mathematics and physics. Um, so this was all from my side, and an interesting viewer can refer to these sources for a detailed account of whatever was discussed in this video. Thank you.